value. For remaining pieces, we could not find their exact value unless you find the matrix product. You have to find the matrix product to find the exact values for other chess pieces. Well, this will not be the case for a rook because one can easily diagonalize the squares for a for a two-dimensional chessboard, and for higher dimensional, we'll apply a component method, which we will be covering. Now, now we will solve this in two ways. We will split the problem in two parts. Number of ways a queen can reach, number of ways a rook can reach h8, starting from a1. This is your h8 and this is your a1. Now, number of ways a rook can reach h8 starting from one corner to the other corner, the opposite corner, in n number of moves. This will be our first problem, and the second problem will delve into higher dimensions. Now let us look into the problem first. So a rook must reach h8 starting from a1 in n moves. Suppose n is equal to 2. Number of ways a rook can reach h8 from a1 is 2 ways. It must move to this corner or this corner, and then it must move here. Since any square from here will make the rook reach h8. So the only way to reach here is to reach this corner or this corner. So for n equal to 2, r of 2 is 2. So there is no way to reach in one move, so r of 1 is 0. R of n being the number of ways the rook can reach h8 from a1. Now let us now a rook. Let us use coordinates. Let's say 1, 1 to 8, 8 is your chessboard. A1, this being your alphabet and this being your number. A represents 1 and H represents 8. Now, you have the coordinate x, y. Now, a rook's valid move will be x star, alpha y, or x beta. Alpha is not equal to x and beta is not equal to y. This is a valid move, and alpha, beta, x and y of course belong to 1 to 8. So a rook starting from x to y can either move to alpha y or x beta. Now, so one can form 3 functions. One can form 3 functions. R1 of n as number of ways a rook changes only one of the one of the components in the end. Say x comma y becomes alpha comma y or x comma beta. This is R1 of n. Now, R2 of n. R1 of n is 1. Let's try that again. The valid move of a chess piece is from x comma y to alpha comma y or x comma beta, since the rook can change either the horizontal or the vertical component. This is the valid move of a chess piece. Now let us now any of the three possibilities can happen. Either x comma y remains as x comma y, or x comma y becomes alpha comma beta, or x comma y becomes x comma alpha, no, alpha comma y and x comma beta. These are the four possibilities after a set of moves. Either the x component will change, y component will change, or neither of them will change, or both of them will change. These are the four possibilities. Let us assume R1 of n has a number of ways. Both of them will change to a fixed alpha and fixed beta. And R2 of n has number of ways. Only one of them will change to a fixed alpha or a fixed beta. And R3 as returning back to the original square. Now R1 of n is number of ways a rook can travel from a fixed x comma y to a fixed alpha comma beta. R2 of n is number of ways a rook can travel from x comma y to alpha comma y or x comma beta, only one of them. And R3 of n as returning back to the original square. Now one can say that R1 of n is now A1 to H8 is the same as A1 to A1 to B3, B2, A1 to C3, A1 to D4, and so on, E5 till H8. That is our assumption, since x comma y to alpha comma beta, the ordering does not matter. So therefore, this is our assumption that A1 to A3, A1 to B2, A1 to C3, A1 to B3, and so on will have the same number of moves. Basically, as long as A1 to any other square, provided they don't have A or a 1 attached to it. Now R1 of n from A1 to H8 is simply nothing but two times R2 of n minus 1 plus 12 times R1 of n minus 1. Now why is this? Because once it reaches here and once it reaches here, it's the same as moving here in one step, because it shares one vertical or one horizontal. Therefore, 2 times R2 n minus 1 comes here. And 12, and since it has not reached H8 already, therefore it's 0 times R3 n minus 1. And R2 of n that means number of ways to move from here to here is how much? Well, how many squares are in between? 1, 2, 3, 4, 5, 6. So 6 R2 n minus 1 plus 7 R1 n minus 1. Since there are 7 squares where it won't share either a horizontal or a vertical square, plus R3 n minus 1. And R3 of n, well, number of ways to move from H8 to H8, it must move back. So it's simply 14 times R2 n minus 1. Now why? Well, once it moves here, then it becomes R2 n minus 1. Since every move will result in either changing either the horizontal or the vertical. It cannot change both. That means it must have, if it moves in the horizontal, then it will have the common vertical component. If it moves in the vertical, it will have the common horizontal component. Therefore, 14 R2 n minus 1. Now, let's explain this again. Now, R1 of n, since now if you want to change xy to alpha beta, right? Now it can change x to 1 to 8 minus x minus alpha, that is that is 6. That is 8 minus 2, 6. Where it's not, we can say x naught, x comma y can change to x naught comma y and also x comma y naught, which again turns to alpha beta. Now x to x naught, where x naught is not x and it's not alpha, so it has 6 different ways and x comma y to x comma y naught, where y naught is not a y or nor beta, so it also has 6 different options. So therefore, a number of ways to move from x naught comma y and x comma y to alpha beta is the same, since both have different horizontal and vertical components. So therefore, 6 plus 6 is 12. So 12 R1 has 12 times R1 of n minus 1 as a sum. And since it cannot reach H8 in one move, therefore it cannot, it must not have R3 of n as a term. And we know that since it has 2 times R2 of n and 12, this is 14. And it can only make 14 moves, so there is nothing left for R3. Now, why 2 times R2? Well, x comma y can change to alpha comma y, or it can change to x comma beta. From here, it can change to alpha comma beta and alpha comma beta. So there are 2 moves in which from x comma y it can reach alpha comma beta or alpha comma y or x comma beta. This is alpha comma y and x comma beta, and this is alpha comma beta, and this is x comma y. So there are 2 moves, 2 squares here, 2 R2 and minus 1. So what we have gotten all 3 equations. Again, we can convert this into a recursive relation. This recursive relation into a matrix. We can diagonalize this matrix and get the exact value. Once we diagonalize, we get that the eigenvalues is 14, 6 and minus 2. That means we can get the exact, and of course the approximate will be 14 power n by 64. This becomes 2 power n by 64, and the dominant term is 7 power n. So 2 power n by 64 times 7 power n is simply 14 power n by 64. Now this is very simple because the rook moves in 14 ways in every square, and there is a 1 by 64 chance that it will reach one of the squares. So it has 14 power n by 64 as the probability. 1 by 64 is the probability that it will reach the square. So 14 power n by 64 is the number of ways a rook can reach H8 from A1 in approximate terms. But we already have the exact value. That is 7 to the power n minus 6 times 7 power n minus 2 into 3 power n plus minus 1 power n. This is the number of ways a rook can reach A1 from A1 to H8 in n moves. Let us put n equal to 1. You get 7 minus 6 minus 1, which is 0. Let's put n equal to 2. You get 2 to the power minus 4 times 49 minus 2 into 9 plus 1. 50 minus 18, which is 32. 32 by 16 is 2. So we get R of 2 as 2. R1 of 2 as 2. Similarly, R1 of 3 and R1 of 4 can also be found. Now, the matrix method has been applied. Now, let us use the component method. Say you have a k-dimensional board of L1 cross L2 till Lk, a k-dimensional board. We have covered k equal to 2, L1 equal to L2 equal to 8 as an 8 cross 8 board. This is what we have covered. Now let us cover the following. Now, assume k equal to 1. You have one component. So you have vertical strip from 1 to L. Now the rook is starting from 1 and it must reach L in n moves. Now every square is adjacent to every other square. If we represent every square as a vertex, then you get a complete graph. Say L is equal to 4. Then 1 is adjacent to 4, 3 and 2 is adjacent to 3, 4 and 3 is adjacent to 4. So you have a complete graph. A complete graph. So a complete graph is represented by KL, where there are L number of vertices. Now a complete graph has an adjacency matrix of 1 everywhere except the diagonal. This matrix is symmetric. So you have J as a matrix of 1s minus I, since the diagonal of adjacency matrix is 0 for a simple graph. So the adjacency matrix of KL is J minus I, where the matrix is L cross L, where you have L cross L square entries. Now, to find the nth power of J minus I, let's find the eigenvalues of J minus I. Assume L is equal to 4. Now, if I put 1, the determinant of J is 0 since the rank of J is 1. Rank of J is 1 since all the rows are repeating. So if I have minus lambda here, J minus I minus lambda I, determinant of this is 0. Now, if I take lambda equal to 1, lambda equal to -1, we end up with the determinant of j equal to 0. So we have one of the eigenvalues as -1 with a multiplicity of 3. Since 3 rows are repeating the matrix of 1s, and 1, the 1 1 1 is the distinct row. Therefore, -1 has a multiplicity of 3, and if we have lambda equal to 3, then you end up having -3, 1 1 1 1 1 1, -3, 1 1 1 1 1 1, -3, -3, 1. If you have -3s instead of zeros in the diagonal, well, then you adding all the bottom 3 rows in the top will give you zeros. Since sum of every row is 0, sum of every column is 0, add the rows, either the rows or the columns, you will have a complete 0 row or a complete 0 column, which gives 3 as an eigenvalue. So lambda equal to 3 and -1 are your eigenvalues with a multiplicity of 3. So the eigenvalues of j minus I is 3 and -1 for 4 cross 4. For L cross L, we have L minus 1 and -1, L minus 1 times. These are the eigenvalues of j minus I. Now, j minus I, well, you have L minus 1 and -1 as the eigenvalues of the adjacency matrix j minus I. So the ijth entry will simply be for I equal to j will be 1 by L minus 1 power n plus L minus 1 times -1 power n. For I not equal to j, we have 1 by L times L minus 1 power n minus -1 power n. Now, this one can observe from this matrix. Take L equal to 4 as an example. Let us show this matrix. You have a 4 cross 4 j minus I and take the square. Well, square of this will give 9 minus 1 on the non-diagonals, and the diagonal will have 9 plus 3. That is 3 square plus 3 times minus 1 square, which is 3 square plus 3, which is 12. And 3 square minus 1, that is 8. Similar, 3 cube plus 3, 3 cube minus 3. 27 minus 3, 27 plus 1, 81 minus 1, 81 plus 3, and so on. So that confirms the result that. Now let us talk about theta. Now in a complete graph, the nth power of the adjacency matrix will give you the number of walks from that square to the others. Now say, what is the significance of the ij entry of the adjacency matrix? Well, the ij entry of the adjacency matrix gives you the number of walks from the ith vertex to the jth vertex.